Hello everyone, so we will be solving February-March 2022 question paper 12 today. Question 21 says a CRO is used to determine the frequency of a sound wave. The diagram shows the waveform on the screen. The time-based setting is 5 milliseconds per division. What is the best estimate of the frequency of the sound wave? 5 milliseconds per division basically means that one division in the x direction represents a time of 5 milliseconds. Since the wanted estimates and the options are pretty far, the values given in the option are pretty far apart, we can go with a rough value. So this is one time period. Let's say I think this is 2.75 divisions. Multiply that by 5 milliseconds. That would give me the total time period, which is 0.01375 seconds. Frequency is 1 over time period. So 1 divided by this value gives me the frequency, which is equals to 72.7272 recurring decimals, so 72.7 Hertz. The closest option that I have here is B. Question 22 is another repeat question from October-November 2016. The question says the warning signal on an ambulance has a frequency of 600 Hertz. The speed of sound is 330 meters per second. The ambulance is traveling at a constant velocity of 25 meters per second towards an observer. The ambulance passes and then moves away from the observer with no change in velocity. Which overall change in observed frequency takes place between the times at which the ambulance is a long way behind the observer and when it is a long way in front of the observer? So the effect that we'll notice, the observer would notice here, is known as the Doppler effect. When the ambulance approaches the observer, he hears a frequency that's higher than the actual frequency. The observed frequency is greater than the source frequency. When the same ambulance is moving away, he hears a frequency that is lower than the actual frequency. Now the formula for Doppler effect is observed frequency is equals to V over V plus minus Vs Fs, where Fs is the source frequency, which is 600 Hertz. V is the speed of sound, 330 meters per second. Vs is the speed of the source, which is the ambulance in this case, and has a speed of 25 meters per second. Now we've got a positive and a negative sign. We use the negative sign when the ambulance is approaching the observer. So we get observed frequency is equals to 330 over 330 minus 25 into 600. And that gives us 649 Hertz. We use a positive sign when the source is moving away. So exact same formula, but with a positive sign, 330 upon 330 plus 25 multiplied by 600, which is equals to 558 Hertz. The question says, what is the overall change in observed frequency? So the change in observed frequency is the difference between the two values, 649 and 558, which is equals to 91 Hertz. Hence, C is the correct answer. Question 23 says, brief pulses of red, blue, and green light are emitted from the sun at the same time. The pulses travel the same distance to reach Mars. Assume that the pulses travel in a vacuum for the full duration of the journey. In which order would these pulses of light arrive at Mars? So let's say this here is the sun, and we've got Mars here, and we've got red, blue, and green light. They're all traveling from the sun to the Mars. Now this is a trick question. Students would assume that it's a difficult question and try to use wavelength or frequency or the time period and figure out which one reaches first. But the time duration it takes for light to reach depends on the distance and the speed. Since they're all light of different color, they have the same speed and they're traveling the same distance, so the time taken would be same. Hence, they will arrive at the same time. So the answer is A. Question 24 says, two coherent progressive waves from different sources meet at a point. Which condition must be satisfied for there to be zero resultant amplitude at the point where the waves meet? The two waves must be emitted from their source with the same intensity. So, even if they are emitted from the source with the same intensity, there is a possibility that one wave travels a greater distance than the other wave. And that would result in them having different amplitudes. So there's a possibility that the resultant amplitude may not be zero. A is hence incorrect. B says two waves must be in phase with each other at the point. That is not a requirement. Once again, they should be out of phase by 180 degrees for a resultant amplitude, and they should have the same amplitude. C says the two waves must be traveling in opposite direction. Even if two waves are not traveling in the opposite direction, as long as they meet, as long as they have the same amplitude and they're out of phase by 180 degrees, we'll get zero resultant amplitude. D says the two waves must have the same amplitude at that point. Yes, the two waves must have the same amplitude at that point. So if one of them has an amplitude of +4 and the other one has an amplitude of -4, as in displacement of +4 and displacement of -4, the amplitude stays 4, they would form a resultant wave of zero amplitude. So D is the correct answer. Question 25 says a corridor is 13.2 meters long and has closed doors that reflect sound at both ends. The speed of sound in the air in the corridor is 330 meters per second. What is the lowest frequency of sound that could create a stationary wave in the corridor with a node halfway along? So we've got a node at the center for sure. We've got closed ends, so we'll get a node here and a node here. And we'll get a waveform like this. Two loops. Each loop, which is node to node, is half a wavelength. So this would be equal to one complete wavelength, 1 lambda. Since 1 lambda here is 13.2 meters, V is equal to F lambda using the formula V is equal to F lambda. V is 330. Frequency is unknown. The wavelength is 13.2. F is equal to 25 hertz. C. Question 26 is, water of wavelength lambda are formed in a ripple tank. The waves are diffracted as they pass through a narrow gap of width d. D is greater than lambda. Which gap, width, and which wavelength will cause the largest decrease in the amount of diffraction? So we want to decrease the diffraction. Since d is already greater than lambda, to get the least amount of diffraction, we would want the gap width d to be greater and the wavelength lambda to be as small as possible. And that would cause the largest decrease in the amount of diffraction. And that here is option C, where the gap width is the largest and the wavelength is the smallest. Moving on to question 27, it says two loudspeakers X and Y emit sound waves that are in phase and of wavelength 0.75 meters. An observer O is able to stand anywhere on a straight line that passes through XY as shown. The observer stands at a point where the sound waves from X and Y meet in phase. What could be the distance OY and XY? Given that at this point the two waves at this point, at point O, the two waves are in phase. So what you need to understand is that for the two waves to be in phase at O, the wave that is coming from Y should cover whole number of wavelengths when it reaches X, because from that point onwards the two waves travel the same distance. So if wave Y is not in phase at X, it won't be phase at O. So how do we find that out? We basically need to find out the number of wavelengths needed to cover distance xy, given that wavelength is 0.75 meters. So 3.5 divided by 0.75 gives us 4.67 lambda. So it took 4.67 wavelengths to reach point x. But that would result in the wave coming from y to be out of phase from the wave that is being emitted out from x. And that would not result in phase waves at O. At 2 points, if xy is 2.75 meters, this is 3.67 lambda. For 2, this is 2.67 lambda. And for 1.5, it's 2 lambda. So wave y completes 2 whole wavelengths when it reaches x. And from that point onwards, the 2 waves move on in phase and are in phase when they reach O. Hence, D is the correct answer. Question 28 says, light of a single wavelength is incident normally on a diffraction grating. The resulting diffraction pattern is displayed on a screen. Which change makes the first orders of intensity maxima further apart from each other on the screen? So the formula is d sine theta is equals to n lambda. We need to increase the angle. If we increase the angle, that would result in the first order maximas to be further apart. And if the value of theta increases, the value of sine theta also increases from 0 to 90. Placing the screen closer to the diffraction grating. Now, changing the distance of the screen from the diffraction grating does not change theta. But what it does is it brings it closer together. So let's say this here is the distance angle theta. So irrespective of where the screen is placed, theta is a constant. But when the screen is placed further apart, the distance between the first orders is greater than the distance when the screen is placed closer. So this would have the exact opposite effect of what we need. Part B says using a diffraction grating with less separation between adjacent scales. So they want us to reduce D. What happens when D decreases? N is 1, lambda is constant. We know that D is inversely proportional to sine theta. Decreasing D would increase sine theta and hence increase theta. This looks like the correct answer. C says using a diffraction grating with more slits but keeping the same separation between adjacent slits. So increasing the number of slits if the separation is same, or decreasing the number of slits if the separation is same, would have no effect. Using light with a shorter wavelength, d sine theta is equal to n lambda. D is proportional to lambda. Apologies. Sine theta is proportional to lambda. D is constant now. N is constant, so sine theta is proportional to lambda. When you decrease the wavelength, sine theta and hence theta also decreases, has the exact opposite effect. D is incorrect. Question 29 says, for a current carrying wire, the current can be calculated using the equation shown. I is equal to A N V Q. What is the meaning of N? Now, N is the number density of charge carriers, which basically means number of charge carriers per unit volume, which is option D. The others are incorrect. Question 30 says, the number of free electrons passing a point in a wire in 24 hours is 6 into 10 to the power 23. What is the average current in the wire? Current is charge flowing per unit time, or the rate of flow of charge. We've got 6 into 10 to the power 23 electrons. The charge on one electron is 1.6 into 10 raised to the power minus 19 coulombs, divided by the total time, which is 24 hours, converted into second is 24 multiplied by 3600. The value that we get is 1.11 amps, which is option B. Question 31 says, in the circuit shown, lamp P is rated 250 volts 50 watt and lamp Q is rated 250 volt 200 watt. The two lamps are connected in series to a 250 volt power supply. Assume that the resistance of each lamp remains constant. Which statement most accurately describes what happens when the switch is closed? Now, it's tempting to say that because lamp Q is rated 200 watts and lamp P is rated 50 watts, lamp Q would have 4 times the power. It's tempting to say that. But that would only happen if both the lamps were provided 250 volts. But that is not the case here. The power provided to the lamps would depend on their resistance. So let's calculate the resistance using the formula. Power is equal to V squared over R. R is equals to V square over power. So for lamp P, the resistance comes out to be 1250 ohms. And for lamp Q, the resistance comes out to be 312.5 ohms. Now we can't use voltage to calculate the power because the distribution of voltage would depend on their resistances. So we'll first have to calculate the voltage that they get, the potential that they get. Or we can go with the other approach. We could instead use power is equals to I square R. We know one thing for sure, that because the two lamps are in series, they'll experience the same current. So power would be directly proportional to the resistance. And we can only do this in this case because they're saying that the resistance of each lamp remains constant. It does not change with the voltage provided to it, with the current. Now, we can clearly see that lamp P has 4 times the resistance than lamp Q. Hence, lamp P will have 4 times the power as lamp Q. So option A is the correct answer. Question 32 says a piece of wire has a length of 0.8 meters and diameter of 5 into 10 to the power minus 4 meters. The IV characteristics of the wire is shown. What is the resistivity of the metal from which the wire is made? So the formula for resistivity is rho is equals to R A over L. Let's find out the resistance. Resistance is the ratio of the potential difference V over I. V is 10 and the corresponding value for I is 5. So 10 over 5, which is equals to 2 ohms. Area pi r, we're given the diameter, half of that is our radius squared upon the length, which is 0.8 meters. This gives us the resistivity as 4.9 into 10 raised to the power minus 7 meters, option C. Question 33. 10 cells each of EMF 1.5 volts are connected together as shown. What is the combined EMF between the terminals X and Y? Now students are prone to make this mistake. They may say that one cell is 1.5 volts. It's 10 cells connected in series, so it should be 1.5 multiplied by 10. 15. That I believe could be the most common incorrect answer. But if you look closely, you'll realize that one of these cells is connected in the opposite way. It's connected in the opposite direction to the other cells. So what we'll do is we'll add all the other cells and subtract this one cell from it. So we've got 9 cells of 1.5 minus 1 cell of 1.5. And that gives us 12 volts. Question 34 says a cell of EMF E and internal resistance R is connected to a variable resistor. The resistance of variable resistor is gradually increased from R to 3R. Which graph shows the variation of the potential difference across the internal resistance, represented by lowercase v, with the potential difference across the variable resistor, represented by an uppercase v? So initially, both the resistors are set to R. So the EMF E splits equally between the two resistors. The sum of the potentials across the two resistors, this V plus this V, V plus capital V at all times should be equal to E, because that is what the cell is capable of providing. Now, when we increase R to 3R, when we increase the variable resistor from R to 3R, the potential across the variable resistor will increase and the potential across the internal resistor would decrease, because potential splits according to the resistance. If you look at the options, you realize that A is the only correct option. Why? Because the potential is increasing for uppercase V and the potential is decreasing for the lowercase v. And at all times, even at this position, at all times, the potential, the total potential is equals to E. So this is 0.75 E and this is 0.25 E. If you look at option B, at this point, This is 0.25, this is 0.25. The combined potential is 0.5 E. That cannot happen. Where does the other half of the potential half E go? If you look at option C, in option C, you'll notice that the potential across the internal resistor has a higher value, which cannot happen. The potential across the external resistor will have a higher value when it goes from R to 3R, hence incorrect. If you look at option D, at this point, 1E, 1E, the total potential is 2E, which cannot happen because the battery is only capable of providing E. Question 35 says, each of Kirchhoff's laws presumes that some quantity is conserved. Which row states Kirchhoff's first law and name the quantity that is conserved? So Kirchhoff's first law is Kirchhoff's current law, which is that the algebraic sum of the currents into a junction is 0. Could be either A or B. And what's conserved? Charge is conserved. So the correct option is A. Kirchhoff's second law, or Kirchhoff's voltage law, basically says that the EMF in a loop is equal to the algebraic sum of the product of the current and the resistance around the loop. C and D. And energy is conserved. But since they're asking for the first law, it's option A. Question 36 says, a cell of EMF of 8 volts and negligible internal resistance. The cell forms part of the circuit as shown. The reading V1 is 4 and the reading V2 is also 4. What is the resistance of resistor R? If reading V1 is equal to reading V2, that basically means that the resistance of these two resistors combined is equal to the resistance of this R. That is the only case where this 8 volts would split equally between the two. So for these two 4 ohms resistor in parallel, the combined resistance is 1 upon 4 plus 1 upon 4 inverse, which is equals to 2 ohms. If these two combine, they're equal to 2 ohm. R should also be equal to 2 ohm. P. Question 37 says, in the circuit shown, the cells have negligible internal resistance and the reading on the galvanometer is 0. What is the value of resistor R? If the reading on the galvanometer is 0, that basically means that the potential at this point is equal to the potential at this point. So you've got a 4 volt power supply. So you've got a 3 ohm resistor and a 9 ohm resistor. So for this top loop here, current flows like this. Because this resistance, 9 ohm resistance, is 3 times the 3 ohm resistance, the potential drop across the 9 ohms would be 3 times. That basically means this one gets 1 volt, the 9 ohm resistor gets 3 volts. So let's assume this is at plus 4 volts and this here is at 0 volts. That would result in a potential difference of 4 volts. That is what the battery is providing. Or you can take any other value as long as the potential is 4 volts. For the other case, let's say this is 9 and this is 0. So after a drop of 1 volt, we're left with 3 volts here. That means we need 3 volts here. That is the only way that the potential here would be equal to the potential here. So of these 9 volts, the only way we can get 3 volts at this point, at this junction, is if there's a potential drop of 6 volts across resistor R. And that would leave 3 volts for the 6 ohm resistor when current flows like this. That is how the battery is placed. If you look here, the potential across R is twice the potential across the 6 ohm resistor, which means that the resistance of R should be twice the resistance of the 6 ohm resistor. So this should be 12 ohms. C is the correct answer. Question 38 says, when alpha particles are directed at gold leaf, number 1, almost all alpha particles pass through without deflection. If you remember the gold leaf experiment, you'd know this happens because the conclusion to this was that the nuclei is very small and alpha particles miss the nuclei. Number 2 says, a few alpha particles are deviated through large angles. And the conclusion to that was that the nucleus is positively charged. So when alpha particles pass close to the nucleus, they get deflected at large angles. So what are the reasons for these? It's option number C, pretty clear. The gold nucleus is very small, so most alpha particles miss all the nuclei. Occasionally the path of an alpha particle is close to a nucleus and hence it deflects. Question 39 says, a nucleus X is radioactive and decays into a nucleus Y. X and Y are isotopes of the same element. Which combination of particles could have been emitted during the decay process? So if X, let's say X, A, B, decays into Y, the number at the top for Y, which is basically the nucleon number, the sum of the number of protons and neutrons, that would be different, but the number at the bottom needs to be B. Now, B basically depends on the number of positive and negative charges emitted. So number of alpha particles and the number of beta minus particles or beta plus particles. If I want this to be same, I need to ensure that the charges cancel out. So it has to be alpha particle, it has to be a beta minus particle, and that's given in the options, alpha, beta minus. Now alpha has a charge of 2 plus, beta has a charge of -1. The only way this could happen is if you have one alpha particle and two beta minus particle, and that would result in the same number of protons, and X and Y would end up being isotopes. This is option B. If you look at question 40, question 40 says a positively charged meson consists of a quark and an antiquark. What could be the quark and antiquark? Option A says charm and anti-up. So a charm quark has a charge of +2/3. An up quark has a charge of +2/3, but this is an anti-up, so this will have a charge of -2/3. The total charge is 0, not positively charged. So A incorrect. Down quark. A down quark has a charge of -1/3. And an anti-top. A top quark has a charge of +2/3, so an anti-quark will have a charge of -2/3. Once again, -3/3, -1. So -1E. So not positively charged. B is incorrect. Strange and anti-bottom. A strange quark has a charge of -1/3, and a bottom quark has a charge of -1/3, so an anti-bottom will have a charge of +1/3. Net charge 0. An up quark has a charge of 2/3. A strange quark has a charge of -1/3, so an anti-strange will have a charge of 1/3. The total charge is 3/3 or 1E, positively charged. D is the correct answer.